All right, guys, we're gonna go ahead and get started. So you, of course, need all of your materials to input this into your notebook. We are going to cut these 2 pages out along these solid lines only, and we are gonna build the same kind of flipbook thing that we put together yesterday. And then we are going to put this on page 24 in our science notebook. And then today we're also going to label page 25 for our bell ringer, just so that we know which bell ringer to work on. And I will write it down in my notes for the day to put that on the website.
What happens if you did both?
Nothing. Then you got extra, you just spent a little bit more time thinking about a longitudinal wave and will be more prepared to answer longitudinal waves questions, which will come in handy when we talk about sound and the difference between sound and light. So we've got those 4. We are going to open up our science notebooks. Page 24, right next to our transverse waves. This will make it really easy. Let me turn the light on. It's pretty dark. This will make it pretty easy to compare and contrast the 2 since they're right next to each other on the notebook, in the notebook. Okay, so this is 24. Longitudinal waves.
Mr. Parrot,
Yes.
my glue stick just broke and I have no other glue stick.
Do you have tape?
I will check.
Okay. Once we have this written down, we're actually going to set this off to the side so that we can set up our notes before gluing them down. So we're going to start with compression and the thing that says glue this part to compression, which is rarefaction. Then I'm going to, remember yesterday, we have this grayed out portion here at the top where it says glue this part to compression. We're going to carefully apply our glue there. Line compression up with the dotted line of rarefaction and press it down to create a flip flap. I'm going to find the one that says glue this part to rarefaction, which is wavelength. Yes, wavelength. Carefully lining that up with the dotted line, pressing it down, and creating that flip flap. And then last but not least, I've got this one here, lining it up, pressing down. Now, unlike yesterday, because I didn't use this as a flip flap yesterday, so I put glue on it and I glued this part down. Today, we are going to use it as a flip flap. So to make sure that I don't put glue on it, I'm going to just pre-fold it up. Just going to pre-fold it so that when I flip it over, I don't accidentally get glue on it. And then I'm just going to use my box cross method to apply my glue so that it stays on the page. I'm gonna get my science notebook. I'm gonna glue that down. And then unflip that frequency flip-flap, and now I've made sure that I didn't accidentally glue it down. Skylar, do you have a question?
Well, it's kind of a comment.
Okay.
Yesterday when we did this, I just went on to today, I went on to page 28, and I just have like compression, rarefaction, wavelengths, and frequency written down, so then I don't have to worry about pulling the flip flaps up if I don't have enough room.
Sure, that's
Is that
fine.
okay?
Yeah, however
Okay.
you want to organize your notes so that it looks best and works best for you, that's fine.
Okay.
Okay. So then getting into our notes, we need to talk about this wave. Now there are some pretty obvious differences between this wave and our transverse wave from yesterday. We know from our last lessons that the reason this looks different is because the movement of the wave, indicated here by this arrow, the particles indicated by these lines are moving in that direction as well. So they're both moving parallel. They're moving in the same direction as each other, and this is what defines a longitudinal wave. Okay, so when we talk about a compression, this is comparable, this is analogous to a part of a transverse wave. Anybody have a guess as to which part of a transverse wave a compression is analogous to? Because we've already kind of said it. We've already done it. When we talked about types of waves, we've already drawn that comparison. Nathan A. and Gavin, yes. Daniel, do you want to tell us what it is? Okay, it's a crest. A compression is very much like the crest of a transverse wave. Now, thinking about what you know about this word, compression, okay, compression, which part of the wave above do you think is the compression? How are you going to determine which part of this is the compression? Susan.
The parts that are like pushed together, so like in the middle.
Exactly. It's the parts that are pushed together or compressed together, because in science we call things what they are. Okay, so I've got my compression. I'm going to label it up top. Is the part where the particles are pushed together. So those are our compressions. Next, we're going to talk about a rarefaction. Well, if the compression is the crest, what part is analogous to the rarefaction? What have we talked about that you could compare a rarefaction to? Daniel, do you want to answer this one before they all answer it in the chat? Okay. Gavin.
A trough.
Yeah, this is going to be the trough. Yeah, this is going to be the trough. Okay. Now, looking at this word, we have a compression is where the particles are compressed. How are we going to identify a rarefaction? How are we going to identify a rarefaction in this wave above?
It's like it's
Emily?
far- Huh?
Is it where the lines are the farthest apart?
Yeah, it'll be where the lines are rare, where the particles are rare, where they are the farthest apart from one another. So right here. So I'm going to draw kind of a little bracket to indicate that these are really far apart. And so that would be our B. So let's add in our definitions here. Let's add in our definitions. Susan told us that a compression is where the particles that make up the medium are close together. So a compression is where the particles of the medium are close together. Whoops. Boys, stop arguing in the chat. And then Emily told us that a rarefaction is where the particles are going to be rare, or where they're going to be farthest apart. So it's the opposite of a compression. Okay, so this is where the particles that make up the medium are farthest apart, where they are rare. I think if I hold it just right, you can read both. Okay, so we already know what a wavelength is. Does somebody want to tell us what the definition of a wavelength is so we can write it down under our flip-flap? Nathan, you. You're going to have to unmute yourself if you want to tell us what the definition is.
One complete crest and one complete trough.
Yeah, so a wavelength is going to be one complete crest and one complete trough. It's the length of that wave cycle. Now, if we're talking about a longitudinal wave, we obviously need to change two of those words. We need to turn them into what? What should we write here for a longitudinal wave?
The compression and
Rarefaction. Yes. Yeah. So it is the length of, it looks like an A, but it's an O. It's the length of one complete compression and one complete rarefaction. So you can think of it as crest to crest, trough to trough, compression to compression, rarefaction to rarefaction. The point is that it is the length of a single wave cycle. Now, thinking about the picture above, thinking about the picture of a longitudinal wave, what is one wavelength going to look like? How are we going to label that? Clayton wavelength is right here. It's one complete compression and one complete rarefaction. Emily.
Would it be like the A and B together?
Yeah, it would be A and B together. So what I'm going to do is we're going to find that middle line. It's easiest to find that middle line in B. That's the lowest point of our wave. That's where the particles are the farthest apart. Okay. Ooh, Daniel, good job with the longitudinal wave in the chat. I like that. Okay. So I'm going to close these down really quick so we can come up here to this question. I'm going to find this middle line here. Okay. This is the bottom part of what would be the bottom part. This is the trough. And then over here, this is that same point a little bit later in the wave. So what I have is this part of this and this part here. Is that one complete wave cycle? Yes, I'm seeing head nods. Yes, it is one complete wave cycle. And so however long this is, that is our wavelength. So we found where the particle was farthest apart here to where the particle was farthest apart here. That includes one complete crest and trough, one complete rarefaction and compression. Let's come back down to the notes, to the definitions part. We're going to label this as C. And then, of course, let's talk about a frequency. You already know what a frequency is. Who wants to tell me what the definition of frequency is? Gavin?
The number of wave cycles per second.
Correct. It's wave cycles per second. Okay. Now, this is a bit of a tricky one because this wave looks so funny. Looking at your wave above, you can see where the origin is, which is the start of that line, and you can see where 1 second is. What is the frequency of this longitudinal wave? Put it in the chat. What do you think the frequency of this longitudinal wave is? Ooh. Ooh. Hmm. 1 second would be the time frame, Charlie. Bailey saying 1, Nathan said 1.5. Interesting, interesting. A lot of people saying 2. Susan's thinking 2. Okay, so let's look at it. Let's come up here, let's label our frequency. This is going to be, this is going to be obviously our label D. Let's label our frequency. Our frequency is obviously going to start here at this origin and end at our 1 second mark. So we are looking for complete rarefactions and complete compressions. How many complete rarefactions do I have? And how many complete compressions do I have? Jillian.
4?
Well, 4 total. How many compressions?
2?
And how many rarefactions?
2.
Okay, so if I have 2 complete compressions and 2 complete rarefactions, what is the frequency of the wave?
2?
2. So all of you that said 2, you are correct. Now, I know Nathan said 1.5, and that was a super interesting guess. Here's what I want you to see. This is the equilibrium. This is indicative of the equilibrium. If I were to find this line, again, I would find it here, where these particles are equal distance apart. Here, where the particles are equal distance apart. Here, equal distance. And then here again, equal distance. So you see we can cross over our equilibrium 4 times. 1, 2, 3, 4. 2 each. We have a frequency of 2.